You're given an experiment to determine how various factors, length, thickness, type, and material affect resistance. You're given this circuit, and basically you're going to change that resistor for various different resistors. Over here you can see that in the first one, the independent variable is the length. I change only the length. Second, only the thickness. Third, only the type. And fourth, only the temperature. And then it becomes obvious. I take R is equal to V over I. Don't rush it, because then you carelessly do it the wrong way around. But generally, most of you did this very well, and you were able to get those 8 answers. Then you can see quite clearly that the longer wire has got more resistance than the shorter wire. That the thicker wire has got less resistance than the thinner wire. That the nichrome has more resistance than the copper. And that the high temperature has got more resistance than the low temperature, which means that the resistance depends on length, thickness, and the type of wire, as well as the temperature. In what direction does conventional current flow? It's from positive to negative. Electron flows from negative to positive, but conventional current is positive to negative. Simple question. A resistor has a resistance of 75 ohms. Calculate the current through the resistor if the voltage is given. You rearrange V equals I over R, and you get R is equal to V over I, and you get I is equal to V over R. Substitute in the values, and you land up with 3,47 amps. Now, in each of the 4 circuits that follow, the cells have a potential difference of 5 volts. You're asked to fill in all the readings on voltmeters and ammeters, and you are expected to know which circle is based on whether it's connected, how it's connected in the circuit. So if it's connected in series, it's a ammeter. If it's connected in parallel, it's a voltmeter. Don't forget to give your answers a unit. So let's go. We've got 1, 2, 3 cells of 5 volts connected in parallel. Cells in parallel act as one cell, and therefore it is 5 volts over the whole system. One cell, 5 volts. Where can they spend all that energy? At the only light bulb here, 5 volts. Then current strength is the same at all points of a series circuit, so it's 7 amps on both sides. Here we've got 1, 2, 3 cells in series, so I add them up. 1, 2, 3 is 15 volts. The current is the same at all points in a series circuit. 4 volts are used by this particular light bulb. They're leaving 11 volts to be used by this light bulb. We add those 2 potential differences when we are in series. Then I've used color here, and I've gone pink from the left until I hit a resistor, and until I hit a resistor. Same thing from the right. And what I notice is 1, 2, 3, 4 means 20 volts. This is connected between pink and green, pink and green, pink and green, pink and green. Ooh. So you find that it is exactly the same energy between those 2 points. These 20 volts need to be used by the parallel system, 20 volts, which means that it doesn't matter if you go to the top branch or to the bottom branch, you're still going to need to use 20 volts. But the current splits, so the 12,2 amps splits, 4,3 amps goes to the top branch, leaving only 7,9 amps for the bottom branch. Calculate the resistance of the resistor. I've been given the potential difference. There's only one thing in this circuit. So in other words, the potential difference here is between pink and green. Again, if I connected over here, I would have 36 volts. And therefore, I'm able to say R is equal to V divided by I, which is 36 divided by 9, which gives me 4 amps. Here we've got a circuit measuring resistance of the wire. Give the function of M1, give the name and function of M1. M1 is connected in series, so M1 is an ammeter, and it measures current strength. M2 is connected in parallel across this particular resistor, and therefore it is a voltmeter. It does not measure voltage, it measures potential difference. Voltage is a bit of a slang in science of just kind of loosely talking about measuring a voltmeter, but the correct terminology is potential difference. What would the effect be if on M1, the current, if the thickness of the resistor was increased. If I increase the thickness of that resistor, the current would get more. It would be easier. Therefore, there would be more current, and therefore the M1 would increase. What if I halved the resistor? That would also become easier, and therefore I would land up with the electrons flowing faster and more current flowing through M1, so M1 would increase. They don't ask for reasons, they just ask you to say what. What is R and its function? This R over here, let's just see if we can clear a bit of space. No. This R over here has got an arrow onto the resistor. That is what is known as a rheostat or a variable resistor. And it has the ability to change resistance. Right, and then it says, what will the effect on M1 be if the arrow R is moved downwards? Now they're giving you a big fat hint to the previous question with moving this downwards. So if I move that arrow downwards, the resistor is going to get longer. And if it's longer, it's more difficult. So what would happen to M1? So that becomes more difficult. And therefore, M1 will decrease. So let's write that out. So it decreases. And there is more resistance. Therefore, less current. You had to have all of that for the 3 marks. Because it does say give a reason for your answer. You need to explain what happens to resistance and what happens to current. Then calculate the equivalent resistance of this parallel network, and the parallel network is very simple. All of them are in parallel, so 1 over R parallel is equal to 1 over 12 plus 1 over 6 plus 1 over 3. Find a common denominator, 12, 1 plus 2 plus 4, and that becomes 7 over 12. That is not the answer. You need to invert it, so it's R parallel is equal to 12 divided by 7, which turns out to be 1,7 ohms. This diagram is working perfectly. It's a complete circuit. The diagram above shows a circuit you might have at home. Switch A is at the bottom of the stairs and switch B at the top of the stairs. What happens when you flick switch A on? Flick that, and what you're doing is you're going to boonk, make a connection over there and break the connection over there. Broken, broken, it turns off. What happens if you leave switch A on and go upstairs and flick switch B? Now you open the circuit there, but you connect it over there. So now you once again have a complete connected circuit. It turns on the light. Why is this circuit so useful? Can control light from 2 places. From the circuit diagram, calculate. So, let's try and do what we need to do here. We've got 16 volts and 10 volts are used over there. So we can put an imaginary voltmeter here and say that's 6 volts. And then we have got some information over here. We've got a 10 volt, and that is also, if I were to put an imaginary over here, it would be 10 volts. There we go. And therefore I can work out the current strength over here. So first says find out the current on A1. So I is equal to V over R, which is 10 divided by 5, which equals 2 amps. Then says, what about A2? Well, since A2 has got 10 volts as well, I'll just put that in there, and I've now got 10 ohms, I can go I is equal to 10 over 10, which is equal to 1 amp. Then I add these together. That's 1 amp, that's 2 amps. When they get together again on the circuit, that is 3 amps. So you add them together, 1 plus 2 equals 3 amps for ammeter 3. Then it says, what is resistor? Well, this is on the main branch, so if I had an ammeter over there, it would also read 3 amps, and I am able to say R is equal to V divided by I. In order to get the potential difference, I would have needed to have said 16 minus 10, work that out. Know that the current is the same at all points in the series circuit, and only then am I able to get that that is 2 ohms. Oh, we're given this long story about changing wires, and she's doing her experiment. Long story short is that we had to work out the gradient of this line. Let's see. Ohm's law experiment by setting up the circuit that is obtained and the results in the table. So you can use the gradient of the graph to calculate the resistance of X, calculate the value. So it is potential difference and current. So it's change in Y over change in X is equal to change in V over change in I, which is great news. Luckily, 0 is a point for me, which makes my life much simpler. And then I can simply say I've got 3 and 1,15 minus 0. So it's 3 minus 0 over 1,15 minus 0, and I land up with a gradient of approximately 2,6 ohms. All of these points were on the line, so you should have got 2,6 no matter which points you used.